I thought I would like to show you here a rather nice device that allows you, say, to solve problems like this if you weren't given the answer in advance. In other words, you see, you'll notice that in our problem, by sort of working backwards, we found that the answer to this problem was inverse sine x plus c. And the question is, what if we hadn't been given this? Is there a way that we could have utilized the knowledge of trigonometry, classical trigonometry, to get a hint as to how to do this? And not only is there such a way of doing this, but the method turns out to be so important that later in our course, in the section called Techniques of Integration, this comes up under the very special name of trigonometric substitution. It works something like this. Whenever you see the sum or the difference of two squares, think of a right triangle. For example, in this case, if I call the hypotenuse 1 and one of the sides x, and call this angle theta, say, the third side of the triangle is the square root of 1 minus x squared. And now, if I think of this way, see, what is the easiest relationship that allows me to express theta as a trigonometric function involving x? See, there are many trigonometric functions, like relationships I can read from this diagram, but it appears that the easiest one is the one that says sine theta equals x over 1. In other words, sine theta equals x. And now you see from this, using differential notation and the like, and again, the technique will be drilled into you, and you'll get plenty of opportunity for using this in the exercises in the text. But for now, I just want you to get to see an idea of how the trigonometry does come back into this. You see, notice that from this diagram I get this relation, now taking the differential of both sides, and notice that I'm working with the ordinary trig functions here, which I allegedly know at this stage. I also know from this triangle that the square root of 1 minus x squared is cosine theta. Therefore, if I make these substitutions in the integral dx over the square root of 1 minus x squared, using the differential notation, dx becomes replaced by cosine theta d theta. The square root of 1 minus x squared becomes replaced by cosine theta. These cancel. The integral then turns out to be what? See, the integral of d theta is theta plus a constant, but what was theta? Theta was what? Sine theta was x, so theta is the number whose sign is x. And you see, notice how the trigonometry comes in and helps us to solve a particular problem. You see, a particular problem that might not have seemed that obvious if we hadn't have used the trigonometry. And again, let me point out where we've used the fact that we're using one-to-oneness. You see, when we drew this particular triangle, we assumed that theta was in the first quadrant. I mean, the angle could have been any place if we're thinking of it as an angle, and knowing the sign only determines the cosine up to a plus or minus. In other words, technically speaking, this should have been plus or minus over here. But the fact that for principal values, theta must be between minus pi over 2 and pi over 2, and since the cosine is positive in that range, that was why we were able to get rid of the negative sign. So again, all I want you to see from this is the fact, and this is very important, that aside from the inverse trigonometric functions being rather important, we can study them completely by giving a short lecture, because everything that we have to know primarily came from previous lectures. The hard part, as is often the case with inverse function notation, is that you may not be familiar with the language that rapidly. You know, I remember I sometimes, when I was first learning, had to think twice about notation like this. Let me start something new here. I'll start at the bottom and work up.